We will now move on to the first plenary talk of this conclave. I request all the dignitaries to kindly step down and occupy the seats below.
Introducing Sri J.D. Patil, I think he doesn't possibly need introduction to this community because most of them would know him. He has been holding very major responsibilities at Lawson and Tubro. Nevertheless, I think it becomes customary for me to introduce him. In fact, I would say that this panel, the topic that we are going to talk is indeed a very good curtain raiser. In fact, he is going to talk on advanced technologies, defense manufacturing industry 4 and beyond. It's really a real curtain raiser for the whole 2-day session that's going on here. One thing I found here is that he was the Indian Space Association founding vice president for the Society of Indian Defense Manufacturers. I think that really qualifies him to give this topic, and it's indeed we are all very fortunate to have him. Of course, the list runs very long, but then some of the key points I would like to mention. He was the member of Executive Committee and Management, and presently is advisor to CMD of Larsen and Toubro. He had many responsibilities like former whole-time director L&T, trustee of L&T Employees Trust, director L&T Semiconductor Technologies Limited, chairman L&T MBDA Missile Systems, and many other accolades here. One thing is that those who have worked in the strategic department like space, atomic energy and defense would know him and definitely would have interacted with him many number of times. With these few words, I have great pleasure to inviting Mr. J.D. Patil, if you are ready to go ahead and then give the lecture on defense manufacturing industry 4 and beyond. To you, Mr. J.D. Patil.
Thank you. Thank you, Dr. Suresh, for a very generous introduction. It's a long journey through Larsen & Toubro, and of course, for me, whether we call it DRDO or DRDL, my first visit to this campus must have been in 87, 88. So I've been coming here very regularly. So is with Trivandrum and Bangalore and many other places. When we talk of industry in terms of manufacturing, we know there are 4 fundamental processes in anything that we manufacture. We either melt and cast, we form, we join, or we cut. Now, all of them really need what was spoken was, if any manufacturing you were to do, you needed to know you can't make a shape very freely, and that's what when Dr. Kakodkar was speaking, manufacturability of your design was the first criteria whether you can ever make it. Now, this shackling of an engineer's ideas actually got at some point in time completely sort of broken when the advances in industry actually came up and when we started talking of Industry 4.0. If we look at those very specific industrial revolutions which have taken place in last about 200 plus years, with the steam and power came the generation 1, and this is when India truly started losing its prowess. This is where the West took over. Industry 2.0 was an extension in terms of making anything in mass manufacturing. Sudden drop from the manufacturing cost to an affordable cost from mass manufacturing. Industry 3.0 saw automation bringing in more and more. And when we all began our engineering career, this is exactly where we were trying to automate at low cost, trying to make things which are more systematized. And of course, then came the smart and the integrated systems of Industry 4.0, where It's only the imagination that now limits what an engineer can do. Anything that can be imagined truly can be produced. So this is a phase of our industrial revolution which now primarily depends on the advances that have happened in the connectivity, the automation, because interconnectivity became extremely important. I mean, if we look at about 3 decades, 4 decades back, computer to computer communication was not so easy. Ethernet made that happen. And unlimited amount of data could go on. Next revolution, 20 years back, and we started seeing what is today we call it the cell technology, cell phone technology. Now this is essentially where the connectivity, just by putting a SIM, any machine sitting here, I can see what is happening in my manufacturing workshops, whether it's in Kadupalli, whether it's in Hazira, whether it is in Talegaon. Now the idea essentially of this connectivity, especially with the security layers, is to be able to see what you do, and each and every parameter of the machine as a result, or for that matter what we are doing, can actually be streamed as a data, and this data can then be analyzed for what we would want to use it for. The machine learning and the real-time availability of this data through a network connectivity obviously made things that we can use AI, and with that now take it forward. So physical marrying of production, operations and smart technologies, that's a confluence that we are really talking about. So there are a few building blocks of what we talk, right from, if we were to look at cloud computing, mobile technologies, machine-to-machine communication, 3D printing, same thing what we call as additive manufacturing, cognitive computing, cyber security, RFID technologies, Internet of Things, big data, and advanced robotics. In terms of machines, which today it's no longer a limitation. Good old days we used to think of a 4-axis and a 5-axis machine, and we used to stop at that. Today, if we want to order a 17-axis machine and 22-axis machine, it is possible. And this is essentially where those advanced machines with the ability to program started making a huge amount of difference. Now, for us at Larsen & Toubro, and more or less similar times as what was happening with the best of the corporations in the country, 1980, somewhere around end of 80s, early 90s, came the times when we changed. We removed every drawing board in every office. Come 1992, 100% of our designs actually moved into what we call as a 3D. Now, when you started moving into 3D, you gave away those limitations which essentially, in terms of special ability of an engineer to think in 3 dimensions, write in 2 dimensions, and then the worker reading from 2 dimensions, trying to convert into 3D, and there used to be a whole lot of mistakes and errors. As long as one was making one part or one component, it was fine. But when you are trying to actually put thousands of components into one small volume, call it a missile, call it a tank, call it a submarine or a warship, now this is where the problem started coming up. Obviously, this 3D designs and 3D models then started moving towards the digital platform, then the virtual reality aspect, because anything that in a complex space we try to put in, there's obviously whether a human being can function, operate, and a man-machine kind of an interface does actually take place. Came the augmented reality, half built, balance half equipment yet to come. Can we actually see that the balance equipment which is supposed to get in be actually now laser projected for the completeness, and then see whether the interfaces are required to be changed, modified, and that's exactly where we now go to full-fledged Industry 4.0. Obviously, there are enormous amount of benefits of this, because before you do anything on the real world, one can actually do enormous amount of optimization. We can minimize the cycle time, and I will quote, if you took on the prototype, or let's say the 4th or the 5th system that you're building or a job you're doing, if you took 100 units of work, it's not impossible to think the 20th or the 50th or the 100th can actually be dropped to 20, 25. So 4 times efficiency of these processes, it actually shows up. Now this is where every possible issue with respect to the manufacture and assembly, one can solve it in the digital domain before one moves into the physical domain. Now once you put it into that physical domain, there are no issues on maintenance, no issues on wanting to make any changes, no issues on anything that you need to thereafter inspect, because inspection is already built in. As you are building, the imagery through computer vision would actually provide for what exactly is the current status with respect to the original design intent. And this is essentially where the back and forth between the technology actually gives you a full-fledged zero rework kind of a situation, 100% acceptable, sort of reaching that truly paperless. And it becomes extremely important because intellectual property and paper don't go together. Anything that is put on paper can always very easily be taken away. What remains in secure domains remains secure. I just want to put one example of what we seen latest, which Dr. Kamath was gracious when he came to our factory. We have broken the world record of anybody who can develop a tank, and that's jointly between DRDO and Larsen & Toubro. From the day we signed the contract, 19 months, the tank is on the tracks. So this is essentially where I'm actually jumping from the basics to what can actually be done. Imagine a situation, anybody in the world today, when he takes about 10 years, 8 years, 9 years to do something, you actually can jump it to below 2 years. Now, the trick again is on the next slide, you see a full-fledged 3D model, and from that 3D model which has 100% of fittings which are going in, then you see it on the shop floor and you see it on the test tracks. So this is the speed, accuracy, avoidance of any amount of waste in the entire manufacturing cycle, and that's essentially where the Industry 4.0 makes its own case. I'll specifically talk of these 6 technologies associated with the Industry 4.0, AI, additive manufacturing, although there's a very separate specific session for it, advanced composites, the digital twin and the power of the digital twin, robotics, automation, AR and VR. Obviously, as I said, reduction in waste, reduction in emission, rework, essentially gaining time and efficiency, cost and optimization. Basic underlying technologies under AI, machine learning, neural networks, deep learning, big data, NLP, cognitive computing, computer vision. Imagine a scenario that we are doing some very complex integration right in a hall of this size and fit it just with 6 cameras. And you don't need any scale, any digital measurement. 100% measurement to an accuracy into few microns, I won't say single micron, one can achieve multiple technologies. And that's essentially where the computer vision, or for that matter the differential GPS, within that closed space and volume, one can actually do. The first example there is typically when you are doing something, there's enormous amount of documentation and tons of paper which all of us generate because of traceability or varieties of issues. Now, whether that is in the form of a technical, legal, techno-commercial or any of those kind of documentation, learning from the documentation for future and extracting specific attributes from that which become useful. So if you did anything once, subsequent time, enormous efficiency can get created. We actually use this. At Larsen & Toubro scale of business, we bid on an average for contracts worth 10 lakh crores every year. Now, when you are bidding 10 lakh crores and you sort of end up having about 3.5 lakh crores of orders every year, human being cannot even read tender documents. Now, tender document is no longer read by a human being. It is read by a machine. The machine tells you, based on the past contracts that it has studied, what is that you would actually accept. There is no need to discuss and debate, either for the customer or for you. Now, that's where the contract cycle times start shrinking and shortening. As a part of business model, an enormously effective tool, basic use of NLP with the AI. Any drawing, we may not have made the drawing, but suppose we have a drawing and then we want to now carry it into 3D domain, or for that matter virtual reality domain. Anything that is written on a drawing need tabulation in terms of dimensions, in terms of tolerances. I am getting into hard manufacturing areas now. Just the monitoring of welding current, precise monitoring of voltage and current, and a smallest of a variation in the voltage or current actually gives rise to the defects. What is seen on the chart, the moment there is a small variation, you actually see on the radiograph a porosity. So you no longer have to now inspect 100% of those RT joints. You possibly need to look at 0.3%, 0.4% instead of spending 100%. And this is the power of the same technology connected through the simple SIM, IoT, take the data out, analyze it in a nice air-conditioned office rather than standing on the shop floor. One worker today in Larsen & Toubro operates 3 machines, 3 welding stations, 1 person. This ratio exactly 20 years back was 3 welders on 1 station. Now that's a 9 times productivity. And this is something which today technology enables by simply using very efficient data availability. And then you see a 1 welding station is not good enough to give you a productivity. You want to make that 9 into 18, put second station, which is what is visible here. Now the moment we want further increase, if you can manage it in terms of the heat and the amount of distortion which will come along with the heat, add a third station. And that's essentially where the world is moving in terms of how to do things better, faster. After you know there is a flaw, you can actually run a proper amount of RT, and through an RT, an output, what man finds extremely difficult to read in RT film, an AI will do it far more efficient. And this is essentially where the judgmental error or the error of judgment which a human being can actually be subject to depending on how fatigued he is. बीवी से झगड़ा करके आया सवेरे. You know, all these scenarios, we know in real life in manufacturing factories, this is what is real world. Now in that real world, any of those issues actually create, although we may have said so and so person did it, we did a building qualification, we did all those kind of things, effectively there is nothing like somebody else checking it, somebody else checking without any human element getting into it. So the defect identification, same way. You have a system architecture, the film doesn't show you anything, but analyze it and it actually shows you where is the possibility of the weakness. Whether that weakness is critical, not critical is a judgment which a human being then can make. But it will show precisely where there is a non-homogeneity and what is the level of non-homogeneity one can actually see. Now when you are doing complex joining, I mean the example is very simple, it's a straight seam that we are seeing on the slide, but instead of a straight seam, imagine it's a very complex seam. It's programmed by an engineer, obviously there can be a proper tracking of that track. Based on the design, you track it and then you keep seeing the track actually moving that way. So today is the era where major big jobs, look at a submarine hull or a warship, overall hull, you actually have the robots which climb on the job. So we call them cobots. Now the cobot actually will do the work without the man going to the job or a job coming to a man. So you can actually leave out that little gadget which will climb up and which will do things. Inspection we know can be done same way we can actually do the manufacturing. So essentially seam location and the actual installation of that seam location on a proper job, how exactly it keeps tracking is there on the slide. I talked of the differential GPS. If you create a precise differential GPS to a much higher order of accuracy, there is no need of any measurement. 100% of shape variations, and this is a submarine hull. You know the error will be on a diameter of in excess of 10 to 15 meters, you are allowed 3 and 4 millimeters of out of circularity, which includes the plate thickness variation. Now when you are trying to monitor 1 millimeter, 2 millimeters, you can actually otherwise do a laser scan, takes its own time to do a scan. Other choice, just use a differential GPS. Wherever you want to measure, take the measurement probe and you know the precise dimension there. Whole field if you want to do it with a laser, and the whole field is available. Data analytics. Now all the data that keeps coming out of what one is doing in the physical manufacturing, call it welding, call it forming when you are doing, forging you are doing, the temperature variations, the forces, the way they are applied. Now each of that data gives rise to some very specific learning, and this learning, obviously initially the models have to learn out of what a human being would do and then start becoming smarter and thereafter tell you precisely where there is a likelihood of a defect. I would just skip through. This is a technology which is amazingly powerful. We decided to invest. Last 3 years we actually have two machines in our own factory. We have actually flown a satellite bus which is printed on a additive manufacturing, and it has been flown this year. Now the scenario with any of these is if you are doing one of two of, the cost is very high. But when you are in mass manufacturing, either you take the restrictions of the, put them onto a design and make it in such a way that cheaper and cheaper methods can do it, or get on to the additive manufacturing. The cost today becomes much higher, obviously because of the powder and the route. But the powder route is not a volume production. So we thought over as what is the other way one can do it without a powder. This is what is powder. On the left side, you actually see a wire. Now you can actually deposit a wire, call it your welding, without a definite boundary to that weld, and the way you will keep depositing, you can build. Of course, the near net shape is not as good as you would do in a powder, but it would be 100 times cheaper. Now, this is the power of technology, just some finishing is needed. Now, what you see on the picture here is actually a product which is created by that wire. Close to that shape, ask for a forging or a casting, you may have to wait for a couple of months. Overnight one can produce it, next day you machine it and the job is ready. 2 days. And that's essentially the speed and power of this technology. And in a completely unconstrained kind of space, one can actually build manufacturing just by using the same age-old what we know. Call it TIG, call it any other process. This is of course not TIG, it's a wire itself being used for melting. The composites, the wonder materials again. Anything that an engineer can think in properties in different dimensions, he can actually put them in place. Now this is essentially where our journey here began with BrahMos, and BrahMos actually gave us the task. Without any transfer of technology, every BrahMos component in composite was tasked to Larsen & Toubro. And that's essentially where we learned the tricks, starting in 98, 25 years now. Now I just want to show you, instead of just the existing kind of regular shapes, what this can do. So you start seeing, advanced composite, unique properties to be built in, right in underwater domain, land, aerospace, and the space, deep space. Now, any of those requirements essentially tell us that a combination of properties when one is looking at is something which actually can be created, and this ability you can do it at a very, very low cost. Now, some of these UAVs that are actually currently we are supplying against an existing air defense contract for the purpose of training of the gunners. You're using a low-cost UAV which flies, you throw it and you train the gunner to be precisely able to hit it. Air defense, good old days, was only based on the shield of lead. It's not shield of lead anymore, you can actually hit it. And the hitting means training, training means wasting something. The moment it becomes expensive, you're putting too much of cost. And that's essentially, some of these we are physically delivering. Sonar domes today, more and more are moving into composites. There's a lot of work which DRDL and us at Larsen & Toubro doing together. We are doing a lot of work. We have a dozen products today in all the four domains in terms of robotics. Digital twin. Once you have anything in operation, how it is going to function, or its data while it is functioning actually being available on land inside your own office or a server, you actually keep monitoring every parameter, run it in the digital twin, and you know, imagine a scenario of a submarine which is actually somewhere else, but whenever it's communicating, it communicates with that data burst. Those data bursts you actually are running on the digital twin. When the submarine comes back, you have what is required to be replaced, available, ready, rather than when it comes on shore and then looking for sending people, then they will inspect, they will find out what is right, what is wrong, they will take all their time. Now, the digital twin is a technology amazingly powerful physically today getting into our warships and submarines. Now, this is where enormous amount of availability of equipment that what one is talking about is being made available. It's the availability of a ship. We remember that when UK decided to sort of give out anything that government owned, as a part of that, they gave out the warship maintenance. And the warship maintenance giving up from the dockyards to the industry actually enhanced the available days at sea. You can no longer say that I need to build a naval dock. They simply now define I need 270 days at sea. Balance 90 days, you want to do whatever you want, you do it. But 270 days, you will be at this day. Now, this is a manufacturing of, digital twin in manufacturing. Now, why this is important? At every stage of manufacturing, we know there are certain processes and certain processes can be sequenced differently. If they are to be sequenced differently, each of that sequence will lead to what? In terms of output, in terms of time, in terms of cost. Now, each of that, or quality for that matter. Now, each of that one can run on a completely digital domain before you go and set up a factory. Now, the moment you do that, either an existing factory one can model, set up a new factory to do this, or an existing factory you now try and change your sequences to be able to get what you want. Now, we know why it is enormously important in defense. We know the customer makes changes in his requirement. Your job is 2/3 done, new change comes in. Now, how do you accommodate that change? It is easy to say it will take now 50% time more. Because some amount of rework, go back, go ahead, all that, where exactly you can save time by resequencing, reallocation of resources, and that's the power of this digital twin on a factory. I just talked of very, very complex robots. This is a robo which in Hazira factory has a 17-axis and it's a welding robo. The entire tank hull gets created in less than 1 day. That's a ability in terms of what you can do. Now, open hull, you can have one robo for that, and the turret part you can have second, and the closing lid you can have the third, and that's it. You can produce many more. Now imagine the amount of cycle time you do it in a conventional way, what it takes and what it can change to with some amount of investment and some amount of right selection of machines. You see some of those robos functional. This is where the first light tank plate was welded, and this was done just 2023. It is now, 22. When Dr. Reddy decided to come one of those days, we said, you are coming, let's cut a plate today. We cut a plate, started welding. Now because everything is there in the digital domain before the job is actually started, now the moment you have that, you don't have to now look at where to start. Any part you pick up and start, and you can sequence it accordingly, and that's essentially where the automation levels are at the global best what we have been able to achieve. 96% of the physical welding in a tank hull can be automated. And the global benchmark there is 75. What this thing shows, from 75 we are able to take. What you still cannot do is a three-dimensional weld. Three directions coming at the corner you still need a human to touch. But short of that corner, because of the limitations of the welding torch and the radius, you can go up to that maybe 10 millimeters, you still need a human being. And that's essentially where we actually can keep moving to how to do jobs better, faster, scale. The factory that we had set up to do 4 tanks a month, when we did the Vajra, we produced 10 per month instead of 4 per month. Dr. Kakadkar talked about the ecosystem. We built a supply chain of 1,700 industry partners, all in 12 months. Now, all 1,700 people, when they are trying to do something, how do you coordinate? How do you ensure that everybody is working on the right part? And that's exactly where everything in the 3D and everything in the digital domain, making or giving access to people in a separate server which is only for the purpose of drawings, and one single reality then prevails right across all those 1,700 people who are doing individual parts, components, subsystems, actually are not working on different things. And this is essentially something one can do with this digitalization. The robotic welding, varieties of them, this is where you can see the robo itself is climbing. All kind of work on the ship hulls, massive ship hulls. And we are using it not only for new building now. The central picture that you see is a refit of a ship. A ship comes for a refit. Now there is a flexibility enough in this robo that if it keeps climbing, you can actually do the descaling and repainting all with this. You are actually flying. What you see on the bottom picture is the drone actually flying inside the tanks, because putting a human being in a tank is extremely risky. Now you fly a drone including dimensions to what is actually wrong with the tank, all of it, one flight inside, and you know that. What you can do outside, you can do inside. Buildings, today we are doing 3D printing. In Bangalore there are few which are existing. We are doing some, our border security force, some of those barracks and their main command center being done with 3D printing. A flight control system in Bangalore was not a 3D but a fast. 45 days, a 7-storied building was built. 45 days, 1.5 months. Now, it does cost about 10%, 15% more, but then the availability of asset for that 1.5 year of construction phase makes up for it. Now, these are efficiency enhancers in that sense, and this is essentially where the technology can take us to. Remote customer inspection. We were the first when the COVID struck. Across industry, I was the president of SIDM then, and the first thing we asked ministry is start inspecting digitally. And I can tell you, we delivered Vajra, which is a tank-mounted artillery gun, completely digitally. 18 agencies used to sit at different locations of comfort of their homes and would inspect a battle tank mounted artillery gun and accept it. Sensors put for the force sensor to check what force you are putting onto an accelerator. And it is possible to do because this is not something utopian, it has actually been done. Now imagine when a man has to physically travel for inspection, he travels one day, does an inspection for maybe 2 hours, second day or third day he comes back. Now all of it he can finish off in the same 2 hours sitting in his office. And he can do 10 times more work. And this is essentially where one actually starts realizing that we need far higher level of pushing on the policy side to enforce, and the best of the organizations who can actually start doing it starts with the institution like the research. If we say it has to be done, it will get done. If you leave it to anybody, nothing will happen. Those who actually want to enjoy with least of the manpower or least of the resources do more, obviously they will use it. In terms of virtual reality, 100% understanding of the job or each and every interference that is likely to happen. We talk of a submarine, typically 2.5 million parts and components get in. You are supposed to have a precise weight, dimensions and coordinates in 3D because each part has to fit in the right place. Now when you are doing it for more than 2 million parts, how do you humanly ever be able to do it? And this is exactly the overall virtual reality what we create can make those things happen. Some more examples of physically a man can create a world around. And that's exactly what you see here. What you see in some of these pictures is the glasses he is wearing, he is actually seeing, and you can actually project it outside with a laser. So you can scan and decide what exactly you produced. So the real component versus your original engineered component, whether you formed, whether you welded, whether you cut, whatever you did, whether the shape is precise. Scan it, compare it with your design. Within seconds, you know it is okay, not okay, requires change in the design end, all of that. The laser technologies today, when we are doing huge amount of ship and submarine hull manufacturing, simultaneously minimum about 3 to 4 of these devices actually keep monitoring the job. The moment it goes beyond half tolerance, you start changing the heating sequence or you start changing where to apply heat more. And this is what the system actually tells you. Even if a guy misses it out, because when you are doing a job which is, let's say, 20 meter by 10 meter or 20 meter by 40 meter, you don't know what is distortion of 1 millimeter, 2 millimeter. This 2 millimeter actually is measured by somebody else. And this is essentially where the system does it. It tells you need to change your heat source, need to move it to so and so place, the accuracy will be better. The modular bridge currently under delivery. We are running the project today exactly 2 years ahead of schedule. Zero man you will see when the testing is done. All IoTized. Every sensor data is available. Nobody is there when the testing happens. Physical moving the bridge there in those many pieces is all that it requires. Thereafter, it's automated. Shipbuilding. From a first hull form in a 3D space to all analysis, or for that matter, anything that you do with it, and I'll flip through few slides, all operational checks, all maintenance checks, all interferences, jigs fixture requirements, shipping routes, how exactly to take it in. Because till the time it is 20, 40, 100 items, a human being can think. The moment it is millions, thousands, tens of thousands, it's not possible. And this is essentially where what is happening inside a compartment now can be watched. Somebody can tell somewhere else, the guy who is doing it there is not right. He is not doing it right. Now, not required. Technically, as a part of the inspection, it would get done. But as it is getting done, you actually can monitor. And that's essentially what you actually see from a 3D to production, vice versa, both ways. From a design server to implement it onto a job, or what is implemented on the job half and balance half is yet being done, how exactly to correlate it. So essentially when you start doing that, you can fit out, and we are today producing warships this way, 80% of the warship is fitted before it is launched. Now again, you can build a warship in 20 to 22 months. Now, you no longer talk of 5 years, 7 years. And that's an efficiency which in a way effectively it delivers. This is an example of what all you can do. A bulkhead, you can fit everything onto bulkhead before the bulkhead goes and gets welded onto the ship. You see a 3D and a real, physically produced, being monitored while it is getting done. And this is the power of fitting out inside. You can see on the left side, whole lot of pipes, cables, which actually takes the most time in shipbuilding. Making a hull is very easy. Now that is essentially what the technology today does. Every operational parameter, integrating interactive layouts, varieties of customer approvals, multiple locations people are sitting, they are able to collaborate. And this ability to collaborate, everybody can annotate, mark, ask for a change. The operator actually says, this is what I would like to be improved, and all gets done, and everybody can see before you may go and physically produce. Same thing for the inspection, same thing for automating those. An entire ship or a submarine compartment, typically a job which takes months to fit out every cleat, every bracket for every pipe and cable. All of it, what you are seeing in this compartment, gets done in one day instead of weeks and months. And just a laser projector precisely projects the coordinates of a point on which the bracket will go, projects an equipment which will get mounted on that, the way the cable would run, the bend radius is proper or not. All of it a computer can tell you. And that's essentially where we can leverage more and more. What I am showing is what is actually done. I am not yet showing what more can be done. And as I said, what more can be done is only an imagination. This is a virtual reality or virtual world on which the more we want to put in, it allows you, because that power of compute is no longer a limitation. You see the cable routings, the way you plan and the way you actually implement, some of it physically there, some of it in virtual. It's not all of it yet there. And you can actually say that if there are 50 cables running at a certain bracket or a certain location, how many has actually run, that's what you see in the blue. And then you see the yellow, which is yet to come in, but projected there. Now the same technology, why only manufacturing? When we talk of defense, we talk of manufacturing projects. Now how do you monitor your projects? The monitoring, again, can be completely done. Today, this is how L&T leverages it. We have world's largest digital implementation, tens of thousands of every asset that Larsen & Toubro uses across 900 sites has been digitized. IoTized, sitting in the office in Mumbai, you actually can see every machine's performance on real time. Machine was started at 5:35 p.m. or 5:35 a.m., how many hours the machine has run, how much load it has carried, every tower crane on a building, what it is doing, every forklift or every machine, every dumper or every JCB, what exactly it is doing. Is it producing? It is not producing. And the data is not for the purpose of policing. The same data is available to 100% people at site. The moment a man sees his own performance, he wants to change and improve. So it's democratization of that data which makes enormous amount of changes, and this is where the project management starts becoming very, very interactive and intense, because you have a system prompting you that you can improve. And that ability to improve comes in because once in a while you may miss it, but now there's somebody who tells you this is the amount of waste, you may like to look at it. So the overall project management then means all designs in 3D, drawings for somebody who still wants to convert it for the purpose of manufacturing, PLM, the life cycle management, the ERP, each and every component with an RFID, with a unique identification. When you talk of millions, you can't identify by any other way. Either you use this or you use a barcode. And then you know individual part, individual component, data science becomes very useful. The whole of statue, the world's tallest and largest statue, each panel of that statue is unique. There are no two panels which are identical, because it's a human figure. Now each panel has an RFID tag. Each is made one. It has to fit in that right place. Now how do you fit it in? And you fit it in 18 months. And that's exactly how you actually use technology to do it. So across shops, across kind of whether you talk of manufacturing, you talk of project, you talk of shipbuilding, you talk of what, one can integrate and use more and more of it. And this is where we actually see unification of your data, unification in terms of what you can do with project lifecycle management. Before the ship or a warship, the submarine comes back, you actually can produce, because you have now a digital model, you have 3D printing machine right in the harbor. You print it till the time the ship comes back, 3 days later, 5 days later, you have a part. Now, no longer an ordering cycle or manufacturing cycle. 100% data is one truth, because nobody else has it. Today, extreme complex and mega projects in the country actually are being run this way. 100% transparently available to the customer. The customer does not have any other database. So the customer, the contractor, the subcontractors, the ecosystem uses one reality, which is the digital reality. And that's exactly where one is going. So there is a customer, there is a designer, and then there is an overall PLM. Now this is where on some of those very complex projects, these are the crisscrossing in terms of what each drawing will mean in real world. Now, the moment you have intelligent data processing, you flip it out, create a central kind of database, and this central database now systematizes information. The takeaway is, even for a simple inode, if it takes 30 days or 20 days, it now happens in hours. It doesn't take days. It doesn't take weeks. And this is essentially, you can put in intelligence inside, creates it. Every component, every piece, now with identification, and of course, the robotic process, you can now automate. Once it is automated, your entire chain, it will prompt whether you want it to take action or not, you decide. And that's essentially where everything is annotated onto a screen, so that when you open your laptop in the morning, you now have a Power BI kind of output. The Power BI tell you where exactly you are. You only need to see what is behind schedule. Or if you had a target that instead of, we promised the customer 2 years, but we want to do it in 18 months. Now is it slipping that 18? You only need to monitor. if there's something wrong, you will keep digging below and keep going deeper and deeper. But absolute top view of what is happening just on one screen. And that's essentially where a guy at the shop floor is confused. Now the same virtual digital reality, he asks a question and there's a chatbot. And the chatbot actually gives you an answer. If you're actually using something, what kind of electrode, what kind of current, what joint, what pieces you are joining, what is supposed to be the process there. Each and every of that, one can get it on a chatbot. Obviously, the latest, some of those very, very complex programs, this is essentially a submarine escape training tower. We did it amazingly ahead of schedule. 100% of this contract was executed purely on these principles. I'm not only talking of physically building inside manufacturing shops now. I'm talking of an entire building and a project and a whole plant inside. All of it constructed and in 30% saving on time. So essentially, if we are looking at what we really have to do, advanced demography, we are someone who are blessed with people. Now, how do we put more and more people? Because more and more intelligence you put in, you can use more and more minds. Second, completely important but unrelated information. IT, we are the world capital. Can we put two together? People and the technology, and that we enjoy that amazing power of putting it together, innovate. And that's essentially where one can start doing things very, very fast, move on to that developed nation. I can't come to DRDL and not show Dr. Kalam's picture. And one of his saying, dream and it works. Thank you so much. Jai Hind.
It was an excellent exposition of Industry 4, which is being practiced at L&T, and I think last almost 45 minutes. It is something like we were dreaming on many of the products that are being done. I think such a nice lecture, we cannot really afford to really leave him without spending another 5 minutes. I think I would like to really engage maybe 2 or 3 questions which any one of you have. We will have an interaction with him. Open to anybody else, Dr. Goel.
Recently, what's happening in Ukraine or say in like there's actually the Russian part. They go like what were thousands of EVs and all that. What is perfect in terms of this product. Do we have in the country a capacity to that extent?
To my mind, the unmanned warfare, very sizably, in our case, the capabilities exist. And
I'm not capacity of the orders like thousands UAVs every day.
no, I tell you why the capacity is not there. Because we always think of the end product. We don't invest into each and every building block. And this is exactly where the drone industry today is suffering. Because we don't produce everything that goes in. And then, of course, you can't use the Chinese.
That's what my worry was actually.
So, essentially, the moment there is a certain size and a certain market, this is where the policy interventions are needed. Because creation of an ecosystem is possible only at some scale. Now, a scale you cannot build today and not use it tomorrow. I think it's essentially something to do with if it is put in, then you must use it. If it is not used, why will somebody put in? Now,
There is a dilemma. The Russians are using actually the 1960 rockets right now, or 70s rockets right now.
correct.
Whereas Israel is not doing that, or maybe Hamas was not doing that.
So the pager is beautiful example of what can be done.
Okay, I think this can be continued. I have one question, Patil.
Yes, sir.
You have really moved in a large scale to digital domain from the physical domain, and also your processes that are being enabled all based on the advanced technology one end to another end. How are you really managing those kinds of skilled human resources? Because that's one of the important drawbacks one will have when you really move from one domain to another, which are all very advanced.
Sir, with this 3D, we started doing something completely different. We stopped recruiting in most of our defense-related plants anybody who is called a workman. There is no workman. Now, you're no longer recruiting an ITI. You actually recruit a diploma engineer who does a complex system-related work. If there's a repetitive, pure skill, somebody else will do it, or you automate it. Now, the robo, if it is going to do the welding, then you don't need a workman. There's somebody who programs it.
Some programming and all those related.
So for this, the lowest common denominator is now is a knowledge resource, a diploma engineer. Okay. So you can find the factories where you don't find workmen, you only have engineers today. And this is how you actually implement more and more technology, because resistance to change in terms of adopting technology starts becoming an issue relating to whether I lose my job. Now you do more with the same one person.
Anybody has last question? Yes, that will be the last question because we are running out of time. Yes, Chaudhary.
The question I am raising, you have shown everything and you have shown the analytics also. Have you put analytics into your system? That is number one. And number two, I find scanning is missing. Scanning to the direct thing, that is missing. Why you are not doing? Suppose you have got a product, then everything can be from the scanning without doing anything straight.
I tell you, there is always a scale issue in defense. If it is a commercial market for which I use, and that's exactly where I brought it on the project side, it's 20 times larger business which actually leverages the same principles, which I didn't talk, but I just showed those 2-3 slides. So that is where it is end to end.
Are you using SAP to manage all this?
Which one?
SAP. Some SAP or that sort of a ERP should be there to manage. SAP, ERP.
That's what I showed. It is basic design, analytical part of it, that's essentially simulation, ERP, including the finance link, payment, a payment gateway gets integrated, it happens unmanned. If the material, because this huge integration that you create out of your supply chain, if a proper material has come and it is going into the assembly, the man gets paid. The system pays it. No human being pays it.
Okay, I think,
auto-ordering is a concept. Auto-ordering gets done. On Akash serial production, we had auto-ordering. Your computer orders. Man doesn't order. RFID is infinite number of cases, I can tell you. RFID is very, very widely used today.
All right,
the entire that statue is an amazing example of RFID.
That's really good. Okay, thank you very much, Mr. Patil. It was really very, very excellent talk, and we have run out of time. I'm sure that there were many more questions people are really looking forward to ask, but then we don't have time. Maybe during the tea time we can discuss.
Thank you. I now request Dr. B.N. Suresh, the session chair, to kindly hand over a memento to our speaker, Sri J.D. Patil. Thank you. And I now request Dr. Samir V. Kamath to kindly hand over a memento to Dr. B.N. Suresh, our session chair. Thank you.